everyone, and welcome. Today, we're going to unravel a pretty fundamental question in chemistry. How in the world do electrons, these tiny buzzing particles, know exactly where to go inside an atom? It all boils down to energy, that invisible force that organizes, well, pretty much everything. So let's dive in and figure out the rules that run their world.
Really think about it. Some atoms have tons of electrons, so what stops them from all just crashing into the nucleus? Or just flying off into space? What tells one electron it belongs right here in this specific orbital and not over there? Turns out, there's a really elegant set of rules that's all about finding the lowest energy and creating a stable atom.
To get a handle on these rules, we've got to start with the simplest atom out there, hydrogen. It's just one proton in the middle and one electron zipping around it. It's our perfect, uncomplicated starting point. No other electrons getting in the way, no complications. Just a simple one-on-one dance between the positive nucleus and that negative electron.
Now, for a hydrogen atom, the rules are incredibly simple. An orbital's energy only depends on its principal quantum number n. You can just think of n as its main energy level or its shell. So if you look here, you'll see that the 2s and 2p orbitals, they're both in the second shell, right? They're at the exact same energy level. Same deal for the 3s, 3p, and 3d orbitals in the third shell. It's all very neat and tidy.
And that brings us to a key term, degenerate. Now, in chemistry, when we say orbitals are degenerate, it's really just a fancy way of saying they have the exact same amount of energy. So in our simple little hydrogen atom, the 2s and 2p orbitals are degenerate. They're basically energy twins. It's a really clean picture.
But what happens when things start to get a bit more crowded? The universe isn't only made of hydrogen. What happens when we have atoms with a lot more electrons and more protons packed into the nucleus? Well, this is where that simple, tidy picture, it starts to get a whole lot more interesting.
And you can see the difference right here. On the left, you've got hydrogen's clean, simple levels. But look at the right. For any atom with more than one electron, those levels split apart. Take a close look at that second energy shell. The 2p orbital now actually has a little more energy than the 2s. And for the third shell, the 3s, 3p, and 3d orbitals are all at different energy levels now. That neat degeneracy we saw before, it's gone.
So this leads us to the most important question, right? Why? Why does just adding more electrons make these energy levels split apart like this? Well, it's because the electrons aren't just dealing with the nucleus anymore. Now, they have to deal with each other.
And the answer lies in that electron-on-electron repulsion. It creates a critical concept called the shielding effect. This right here is the secret to understanding the energy layout in pretty much every other atom.
So, what is this shielding? Okay, imagine you're an electron in an outer shell. You're trying to feel that nice, strong pull from the positive nucleus. But there are other electrons in the inner shells right between you and the nucleus. And since they're also negatively charged, they kind of push you away, and they block or shield some of the nucleus's positive charge. It's like they're a pair of sunglasses cutting down the glare of the full nuclear pull.
And the result of all this shielding is what we call the effective nuclear charge, or Z-effective. Think of it as the discounted, net positive charge that an outer electron actually gets to feel. Because of that shielding, Z-effective is always going to be less than the actual full nuclear charge, which we just call Z.
Now, here's the kicker. Not all orbitals get shielded equally. It all depends on their shape and how well they can penetrate or sneak past those inner electron clouds. As you can see, a spherical s orbital is really good at getting close to the nucleus. It spends some of its time inside the inner shells, so it feels a stronger pull. A p orbital penetrates a little less, and a d orbital even less than that. So here's the bottom line. The better an orbital penetrates, the less it's shielded, the tighter it's held by the nucleus, and the lower its energy is. That's exactly why the 2s orbital has less energy than the 2p.
Okay, so now we get the why behind the energy splitting. But is there an easy way to predict the energy order of all these orbitals without having to think about shielding every single time?
Oh yeah.
Absolutely. It's called the N+L rule, and it's a beautifully simple little tool for getting everything in the right order.
The main rule is surprisingly simple. For any orbital, you just add up its principal quantum number, n, that's the shell number, and its azimuthal quantum number, L, which just tells you its shape, where s is 0, p is 1, d is 2, and so on. The orbital with the lowest total sum has the lowest energy. That's pretty much it. Let's actually try it out with the table here. Let's compare the 4s orbital and the 3d orbital. For 4s, n is 4, and since it's an s orbital,
L is 0. So 4 plus 0 gives us a sum of 4. Now for 3D, N is 3, and for a d orbital, L is 2. So 3 plus 2 gives us 5. Since 4 is less than 5, the rule perfectly predicts that the 4s orbital has lower energy and fills up before the 3d orbital does. It works.
But you might be wondering, what happens if there's a tie? And that's where rule number 2 comes in. If two orbitals have the exact same n plus L value, the orbital with the lower n value wins. It gets the lower energy spot. So for example, a 2p orbital has n equals 2 and L equals 1, so n plus L is 3. A 3s orbital has n equals 3 and L equals 0, so n plus L is also 3. It's a tie. But since the 2p orbital has the lower n value, 2 versus 3, it has the lower energy.
So let's just take a second and recap the big ideas we've covered. We went from the simple case of hydrogen to the more complicated reality for all other atoms, and we found a really handy rule to make sense of it all.
So here it is, your atomic energy toolkit. Remember, for hydrogen, it's simple. Energy just depends on the shell number n. For everything else, that electron shielding effect splits the levels apart. And to predict the new order, we use our awesome two-part n plus L rule. First, you find the orbital with the lower sum of n plus L. And if there's a tie, the orbital with the lower n value wins.
And that really brings it all together. This set of energy rules isn't just some abstract idea. It is the fundamental blueprint that tells us how electrons fill up inside an atom. And that, in turn, is what explains the entire structure of the periodic table, why it looks the way it does, and why elements in the same column act so much alike. So the final question is, if this simple energy blueprint can explain all of that, what else in the world of chemistry could it unlock?